Okay, these are examples of the motion of objects on inclined planes. The first example is a box of mass 10 kilograms placed on an inclined plane at an angle of 30 degrees with the horizontal. First thing we want to do is to draw a diagram. So this is going to be my plane, okay? I'm going to put a box of mass 10 kilograms on this plane, and it will be at a 30-degree angle with the horizontal. Okay. Part B, determine the weight of the box and draw its vector. The vector will be drawn straight down, okay? And the magnitude of this vector can be found by m times g, which will be 10 times 9.8 or 98 newtons. Okay, part C, break up this weight vector into components perpendicular and parallel to the plane. So I'm going to take this weight vector, I'm going to draw a couple of components. One of them is going to be perpendicular to the plane, and the other is going to be parallel to the plane. Note that these two vectors form a right angle, and the weight vector is the hypotenuse. Now you can show with geometry that this angle up here is the same as the angle that the plane makes with the horizontal, 30 degrees. These two triangles are actually similar. Okay. Alright, I'm going to label these vectors force perpendicular and force parallel. So those are my two components. The weight vector can be broken into components perpendicular and parallel to the plane. The weight vector is the resultant of those two components. Okay, now I want to use SOHCAHTOA to determine the magnitude of these components. Well, in no particular order, let's do force perpendicular first, and that's the adjacent side of my vector triangle, so I can use the cosine function. Cosine is equal to adjacent over hypotenuse. Multiplying both sides by 98, and operating my calculator, I get an answer of 84.9 newtons. The force parallel is the opposite side, so I'm going to use a sine function. Sine is opposite over hypotenuse. After multiplying by 98, turns out to be 49 newtons for that component. Okay, put them on my diagram here. Next, if the plane is frictionless, the box will accelerate down the plane. What is the magnitude of the force that pushes the box down the plane? Well, the box is going to accelerate in that direction, so the force must be in that direction, and we already know what that force is. It's 49 newtons. It's force parallel. It's pushing the box down the plane. So the magnitude of that force is simply, by inspection, 49 newtons. Next part, determine the acceleration of the box down the plane. Well, we can do that with Newton's second law, F equals ma. Solving for acceleration, inserting my values, and the calculation is easy, 4.9 meters per second squared for the acceleration. Okay, next, what is the normal force? That is, the force pushing the surfaces together. Well, if this box does not move into the plane or off the plane, that means the normal force and the force perpendicular are equal. By definition, the normal force is the force being exerted perpendicular by the surface onto the box. And so, since it's an equilibrium in that dimension, the normal force is the same as force perpendicular, magnitude-wise, so it's 84.9 newtons. Okay. It used to be that the normal force is the same as the weight. That's only true on a horizontal surface. When we're on an incline, we need to calculate the components, and the normal force is the same as force perpendicular. Now, let's say there's friction. If the coefficient of friction is 0.35, what is the force of friction? Well, force of friction, which it will be directed up the box, up the plane that is. The magnitude can be found by mu times the normal force. And the normal force is now 84.9 newtons. And so multiplying it out, we get 29.7 newtons of friction force. Okay. What is the net force pushing the box down the plane? The net force is always the vector sum of the forces acting in a particular dimension, which I will take to be parallel to the plane. There are two forces acting in that direction, the force parallel, pushing it down the plane, and the friction force opposing that. The net force will be the vector sum of these two. Taking the downward direction to be positive, that makes the friction force negative, and algebraically that adds to positive 19.3 newtons. Lastly, what is the acceleration of the box down the plane under these conditions? Okay, well, Newton's second law says that the net force is equal to the ma. Solving for the acceleration, we get the net force divided by the mass. Inserting my values, and the calculation is easy. It's 1.93 meters per second squared. Okay, example number 2. A 40 kilogram box is placed on an inclined plane at an angle of 20 degrees with the horizontal. Determine the components of force parallel and perpendicular to the plane. Here's my sketch. 20 degree incline. Okay, 40 kilogram box. I'm going to find the weight of this box, okay, by m times g, which 392 newtons. I'm going to break that weight vector now into components. Perpendicular to the plane, parallel to the plane. These form a right triangle with weight as a hypotenuse, and the little angle in here is 20 degrees, same as the angle of the incline. Okay. To find force perpendicular, which is the adjacent side, I'm going to use the cosine function. Multiplying both sides by 392. My calculator said 368 newtons for force perpendicular. The sine function can be used to find force parallel. Multiplying both sides by 392. My calculator said 134 newtons for the parallel component. Okay, so break up the weight, or the weight vector acts straight down, and then break it up into perpendicular, parallel components, and then use SOHCAHTOA to determine the magnitude of those components. Okay, next example. I have a box of oranges placed on a ramp. Okay, so here's my ramp, 25 degree incline. Okay, 15 kilogram box of oranges. The friction coefficient is 0.5. We want to know, will the box slide down the plane? Okay. Well, it will slide down the plane if there is a net force in that direction. Okay. That's what we have to find out. Okay. Will there be a net force? All right. Well, I'm going to take the weight of this crated box of oranges, 15 kilograms, has a weight of 147 newtons. Okay. We are going to now break that weight vector into components, force perpendicular and force parallel. Okay. I can find the magnitude of these, okay, by cosine function for force perpendicular. And the perpendicular component was 133 newtons. Force parallel can be found by the sine function. Okay. And my calculator said 62 newtons. All right. All right, so I added those to my diagram. Now, there's a coefficient of friction here, so I know that there's a force of friction. Okay. I have 62 Newton force pushing it down the plane. All right. Is that enough to overcome friction? To find out, we need to find the force of friction, which we can do by mu times the normal force. Mu times the normal force, which is now force perpendicular. Okay. All right. And that turns out to be 66.6 newtons. Now, does the box slide down the plane? And actually the answer is no, because the force of friction is greater than the 62 newtons. Okay? And therefore, this 62 newtons of parallel force is not enough to overcome friction. So the box does not slide down the plane. Okay? And incidentally, in this case, I misspoke a little bit in that the force of friction is 66.6. This is actually a maximum value for the friction force. Okay, the force of friction, if you push on something but it's not hard enough to move it, the force that you apply is actually the force that friction opposes it. Okay, so this friction force, 66.6 newtons, is actually the maximum amount of force that will oppose this motion. If force parallel was greater than this, then the force of friction would be 66.6 newtons, but there would be a net force down the plane. Okay, so to be strictly correct, the force of friction in this case is actually the same as force parallel. Okay, the answer is the same. The box does not slide down the plane. Okay, but just to be strictly correct, the friction force can never be larger than that. Okay, all right, next example. A 25 kilogram box is placed on a 40-degree inclined plane. Determine the acceleration of the block down the plane. Okay, we have a lot to do here, but first of all, let's find the weight vector. Okay, m times g, 245 newtons. All right, now we're going to break that weight vector into components, perpendicular and parallel to the plane. The angle is the same as the incline, remember. I'm going to determine the magnitudes of these components with SOHCAHTOA. So cosine is force perpendicular over the hypotenuse. 187.8 newtons there. Force parallel will be found using the sine function. 94.5 newtons results. Okay, now we have a friction force, and we can now determine what that friction force is by mu times the normal force, which is the same as force perpendicular. That turns out to be, in this case, 37.5 newtons. Okay. Now, I can see that there will be a net force down the plane in this case, because 94.5 newtons pushes the box down the plane, 37.5 newtons opposes that. So the net force will be the vector sum of the forces acting in the dimension down the plane, force parallel, and the friction force. I'm going to consider down the plane as the positive direction, so that makes the friction force negative in magnitude. And the net force ends up having a value of 57 newtons, positive. And then finally, I can use Newton's second law, F equals ma. Solving for the acceleration, putting in my net force, and my calculator yields a result of 2.3 meters per second squared. Okay, lastly, we have this interesting example. Okay, we want to determine the acceleration of the box on the plane. Now, we're not sure quite whether it goes down or up yet. Okay, we have to figure out some things. All right, now, if it moves, it's because of the weight. It is because of the weight of this 80 kilogram box. Okay, which turns out to be 784 newtons. And that is transmitted by the string to this box. So there's a 784 Newton force pulling that box up the plane. Okay. Now there's also another force we haven't drawn yet that pushes it down the plane, and that's due to force parallel. The weight, the parallel component of the weight of that box, the 25 kilogram box on the plane. We need to figure out what that is. To do that, we first have to figure out the weight of the 25 kilogram box, which turns out to be 245 newtons. Then I'm going to draw in my components. 30-degree angle, same as the incline. And I can determine the values of these, the magnitudes of these components. Cosine for force perpendicular, which ends up being 212 newtons. For force parallel, we use the sine function. Ends up being 122.5 newtons. Okay, so inserted the values in here. Okay, now I actually know that the friction force, well, we can find the magnitude of the friction force to be 42.4 newtons, okay, by mu times the normal force. And I actually know that that friction component is going to be acting down the plane. And the reason I know that is because the applied force acts up the plane of 784, force parallel acts down the plane, and 784 newtons wins, right? So So this box is going to be pulled up the plane. So friction is actually going to oppose that. I also know that the net force is actually up the plane, actually. Okay, so I could have taken that out. Anyway, I can find out what that net force is. Okay, the net force will be the sum, the vector sum, of the forces acting in the dimension parallel to the plane, of which there are three: applied force up the plane, parallel force down the plane, and friction acting down the plane. So the net force will be the vector sum of those three. I'm going to consider the positive direction to be up the plane. Okay, that makes both force parallel and the friction force negative. And then when I add these algebraically, it turns out to be positive 619 newtons. And then I can apply Newton's second law, F equals ma. Solving for the acceleration, putting my values in there, and ultimately it turns out to be 24.8 meters per second squared up the plane, or positive.